Hi guys, if you've been following our channel, you know that recently we've rebooted our Physics for Martial Arts video series. This is something we started 3 years ago, and back then we were taking a more detailed look at the physics equations and the mathematics that was involved. Not too detailed because I didn't want to get overwhelming, but we were looking more at the equations. This time around we're taking a conceptual physics approach. And so today I want to summarize some of the physics that's involved in the first two lessons that we released. The first one was on impact force. This previous one was on impact time. So we are going to look at the equations again, but I'm going to do an abridged version, sort of a Cliff Notes version. So if you want a more detailed explanation, I'll include some links in the description to some of the previous videos from back 3 years in the past. So the first thing that we looked at was impact force. There's an equation that people mess up all the time. They misinterpret it. We're going to look at it in a second. That equation, a misunderstanding of that equation also leads to a misunderstanding of the role that impact time plays in determining impact force. Many martial artists, not all martial artists, but many that have seen the equations that we're going to look at, have misinterpreted what they mean, and as such, there's plenty of martial artists that believe by minimizing impact time, by snapping your punch back in a way that minimizes impact time, you're going to thereby maximize impact force. Now let me start by saying there's plenty of reasons to snap your punches and kicks, various strikes back rapidly. There's plenty of reasons to motivate that action. However, it would be inaccurate to do so for the sake of maximizing impact force. That's just wrong. You cannot maximize impact force by minimizing impact time. And I'm going to show you what the physics actually says today. So, first thing that people mess up, it's F equals ma. Newton's second law, right? Well, actually, this isn't really what Newton said. I'll clear that up in a moment as well. But F equals ma, when people see this equation, they look at it and they say, if we have a mass and it's accelerating, then this is the force that that mass can actually deliver. This is the force that mass has. So if we have so much mass that's in motion and it's accelerating at a certain rate, then this is the force that we can deliver into our opponent. And if we can increase our acceleration, we can increase the force that we're going to deliver. Now that's just flat out wrong. That is a completely inaccurate representation of what this equation means. And I'm going to prove it to you with a very simple thought experiment. Imagine you're laying on the floor right here in this room. And I have two 5-pound weights, and I hold one an inch above your body. And I have somebody else on a ladder holding another one right up against the ceiling. And this is probably an 8-foot ceiling or so. If this interpretation is correct, well, all objects fall with the same acceleration due to gravity, or at least within this environment, that's a reasonable assumption to make. There's, of course, there's certain limitations to this particular theory. So with these two weights, it's reasonable to assume they're both going to fall with the gravitational acceleration constant, 9.8 meters per second squared. Now, we're going to say they're identical weights in every way. They have the same mass. They have the same acceleration. Now, if you had to choose, for whatever reason, I know it doesn't really make sense, but you're put in the position that you have to choose. One of these weights is going to be dropped on you. Which one do you choose? Well, if the interpretation that I presented at the beginning is correct, it shouldn't matter because both weights have the same mass and the same acceleration all the way through the fall. So it should not matter which one you choose because they should have the same force upon impact. We know that's not true. We know you're not going to choose the weight that's up against the ceiling. Why? Because it's not actually this equation that tells us the force that a mass is going to deliver. This equation could help us determine the force that was delivered. Because what is this really telling us? It's telling us that if a net force is acting on a mass, that it will cause that mass to accelerate. That's a more appropriate way to write this equation, but this still is not what Newton said. Newton didn't say F equals ma. Newton actually essentially said that the net force is equal to the time rate of change of momentum. That's a fancy way of writing it. We could write this differently. The net force is equal to the final momentum minus the initial momentum divided by whatever time period it took for the momentum to change. Now the next question you might have, if you haven't been following our other videos, is what is momentum? Momentum is mass times velocity. So what Newton said is that if you have a mass and it's in motion, that mass wants to remain in motion unless acted upon by a net external force. If you have a mass and it's at rest, that mass wants to remain at rest unless it's acted upon by a net external force. That's Newton's first law. This is Newton's second law. And so it's basically the mathematical representation of that law. If there is a net external force, there will be a change in momentum. So now we've arrived at essentially the equation here. We could write this with another sign. So we're using a sigma. That means you're adding all the forces together. And we're going to now use a delta, a triangle, which means if there's a change in momentum, there's some difference in momentum. This means subtract the final and the initial and divide it by whatever the time period is. So we're adding up the forces that are acting on the mass, and if there is an imbalance in force, if there is a net force, the momentum is going to change. It's this form that sometimes leads to confusion. Because what this also says, mathematically, what this says, but we have to look at the mathematics and interpret in the physical sense what is possible. Sometimes what's possible with math is very different from what the physical world actually presents. If you decrease this variable, if you decrease the time, mathematically speaking, we have a number here. If we reduce this number goes up. So this is where some have said, okay, well, we need to minimize this number. But the problem is they're still locked into the mindset that this is this, that whatever we get here is the force we're delivering. It isn't. We have to look at a collision in this case. There's a collision between our mass and our opponent. And if we simplify it and we just look at a collision between two masses, and let's say it's two masses that maybe are in a frictionless environment. And you can actually achieve this in the lab. When I was in school for physics, we had air tracks that could, not perfectly, but pretty darn close, achieve a frictionless environment for the sake of seeing if these equations actually work out. Now, I know some will say, well, see, it works in a lab, but it doesn't work in real life. But what we're understanding about the principles of physics, the laws of physics, in basically, if you study Kempo, in the ideal phase, helps us develop a conceptual basis, a foundation to build upon when we start adding the complexities of the real world into things. So if we have a mass that's moving this way and it collides with another mass, there's one final law that Newton said. Newton's third law of motion, at least. He said that for every action, basically for every force, there's an equal but opposite force. So when these two objects hit, there's going to be some change in momentum. And if we look at this object or this object in this environment, when they collide, because the only forces that are at play are the forces of impact, we could choose either object, we could do this equation, and we now know the force of impact. Let's look at our situation. If I'm throwing a punch and I decide to rapidly withdraw that before it reaches its natural end. Now, I'm not telling you that you should let every strike reach its natural end, meaning I'm not going to keep punching and forcing through until my opponent brings my strike to rest. That's just not what we do in many instances. Maybe sometimes we do, but sometimes we don't. But if that were the case, if I did let my strike, my mass hits my opponent and it reaches its sort of natural termination point where it comes to rest, then this equation somewhat gives us a conceptual basis of what's going on. Obviously, things are different when you start looking at biomechanics, but the same laws are involved. Now, If I withdraw that punch before it reaches its natural end, what this is telling us is this goes up. But what people interpret it to mean is this goes up. It's not the force you're delivering that goes up, it's the net force causing the change in momentum on your mass that goes up. So in that case, it's now as if this mass is about to crash into this one, and I have a cable that's attached, and the moment of impact, I yank that cable back. What caused that change in momentum? Well, we could call this FT, maybe there's some tension cable, and we'll call this FM. I know this is probably very sloppy and you can't fully read it, but Newton's law would read FT minus FM. There's a net force. That's what it is. It's not this. Now, if I've lost you mathematically, again, there's a simple conceptual illustration to this that I presented in yesterday's video. And that is, our objective is to slam a certain amount of mass into an object. That object, in this case, is our opponent. We're trying to do damage to our opponent. If you take a car and you slam on the gas and you continue to accelerate into the impact, you're going to cause a certain amount of damage. Now, let me ask you this. If you take that same car, in the moment of impact, you're slamming on the brakes, are you going to cause more or less damage to whatever you crash into? The answer is less, because now you have an internal force that you're bringing into the system that's acting to assist in achieving a change in momentum. So that didn't exactly turn out to be the Cliff Notes version I wanted. Perhaps I went into just as much detail as I did in the previous video. Either way, I'll still include links so you can check it out. A little background on why I started this series. I have a passion for physics. Originally, I was going to school to be a physics teacher, and I ultimately realized I could run a successful full-time dojo. And so I still revisit my physics. I occasionally just pull out a physics textbook and solve some problems, just because it's one of the things, at least mechanics especially, is one of the things I really find fascinating. Hopefully you find this interesting as well. If you've made it this far, hopefully you find it interesting. This isn't a series that's for everybody. It's for those of you that want to understand a little bit more of the science behind the martial arts, and hopefully along the way, in exploring some of the science, you'll understand some of the misconceptions and you'll have a better understanding of what's actually going on. That being said, we are continuing with our conceptual physics series that we're currently working on. We have another episode or two that's in the works. But if you have any questions, if there's anything you'd like to see covered, please leave a comment below and we'll try to get to it if we can. All right, that'll be it for this video. Let me know if you have any questions, and I'll see you soon. Take care.